like that in, or could it be sand made up of those little grains that's still lime? So you convert that from a lime sediment to a limestone, you know, it's the same thing. So this rock is both because of that thing. Of course, in terminology, we have a lot of fancy terms for stuff like that. So we call this calbarenite because the word calc is for calcium, and arenite is the Greek term for sand. So you can kind of combine things like that. So I just wanted to mention that because any terms you use sometimes it's kind of confusing. But just remember that in this case you can use several different terms for this.
Aeolianite would be another term that you could use.
Well, the aeolian is the Greek word for wind. So these originate. So that's a genetic term rather than more of a descriptive term, because you can interpret it as being formed as a wind-blown sand, as a sand dune. The aeolian would be the deposit. ITE makes it a rock. And that's what happened here. Another term we use for this is lithified. The term lith is a word for, a Greek word for Latin for the rock. So rockified or lithified, you know, change it from a sediment to a rock kind of thing. So those are just terms you hear a lot. Lithified sand dunes. That's a good description for that, you know. Or aeolian. If you use the term aeolianite, most people are going to go, what? You know, so you have to define all this terminology. So now the other really fascinating thing here, and I'll go through this hopefully not too tortuously, is this is only one small location where this limestone occurs all the way along the coast. You go back down by the Hyatt Regency Hotel, which is the last resort you saw before you hit the gravel road coming out here, and actually all the way to as far as you can see here on the coast, and then around that point to another bay, there's a major amount of limestone all the way along this coast. And so I've mapped all of this stuff, and you can see the different colors of red, green, there's some orange in here, and there's some blue and purple. All these colors represent different units of limestone along the coast. And they're not all the same age. There's a lot of variation between them. And a map like this, for geologists, the map is like it's really a key piece of data. If you can go out and find rock and map its distribution, that's a really good start in terms of understanding its origin, which is one of the objectives, of course, of doing it. So the geologic map is a critical piece of information for any geologist looking at that. And sometimes you have to create your own maps, which is you go out and you find the rock and you go to where you don't find it anymore and you put a line on the map. That's the edge of it. You can just follow that around where it is and it isn't. And you can find that there's a very interesting distribution where it turns out it occurs all along the coast here. Now, it turns out when I mapped it, I thought, well, there's a lot of limestone here, but I started discovering there's a lot of changes in the limestone, and the changes are noted predominantly by red layers like this. And so when I started accumulating all that into a composite vertical profile of this, I tried to create what's called a stratigraphic column. Strata mean, you know, layering, and so or geologic section. And so this kind of tries to show sort of not quite to scale, but it shows the oldest lava rocks on the island in up to 5 million years. It shows the volcanics that are from the Kaaloa series, which is the younger, rejuvenated. And at the top of that, there's a red soil, which is a weathered zone at the top of the lava rock. And then the yellow represents the limestone sitting on top of it. And then the limestone actually has at least 4 different units separated by reddish soils. The difficulty is that they don't stack up in any one place altogether. They're spread out along the coast. So the young ones are down here and the older ones are up there. But you can start trying to tie them together by other properties. The fact that limestone as it gets older, it gets harder. And it gets more dissolution, more dissolving and re-cementing. So you can use that as well. But the relationships between the layers are very important. So these reddish zones turn out to be soils, soil zones. And so you wonder, like, well, and they're full of land snails and plant roots. If you look at these carefully, you'll see that there's no real layering in it. It's all kind of burrowed up with the plants and the organisms that live in it. They're very massive, very fine grained, and they're predominantly silt and clay material with some lime cementing them. But they represent major breaks in that. Well, the fun part is what this all means in terms of its geologic history and accumulation. And we know that when the sea level is at this stage, which is a relatively high stand of sea level, it's about the highest it's been for 100,000 years. So we're at what we call a high stand. And about every 100,000 years or so, the sea level drops down as much as 400 feet or so, 120 meters, which is called the low stand. And that's a normal cycle on the planet that's been recognized for about the last 1 to 2 million years throughout the Pleistocene. So, and that's related to global heating and cooling, probably a celestial navigation, or celestial mechanics kind of thing in terms of where the Earth is in relationship to the Sun over a very long periodicity. So it's been worked out in many different ways. A guy by the name of Czechoslovakian by the name of Milankovitch came up with a mathematical scenario of celestial bodies rotating to work that out. So it's commonly called Milankovitch cycles, and that, or just other kinds of cycles. If you look at a plot of sea level change, just back to about 140,000 years, here this is from 0 down to, that's 100 meters right there, or about, so that's 400 feet, about 120 meters. So this is sea level change over the last 140,000 years or so. You can see right now we're here, and actually a couple thousand years ago sea level was about 2 meters higher than it is now. And it dropped back down. Of course we know now it's rising slightly. But if you go back 18,000 years ago, sea level was about 400 feet lower. And if you go back to 125,000 years ago, it's where it is now, again. And you see that it dropped down in a very regular way and then rose quickly. So that's just the last 140,000 years. So when sea level is high, the beaches are here, the wind's blowing the sand down the coast and it's building sand dunes. So when sea level is low, and I've got a little diagram here that shows what the island would look like if sea level was low. This is, the light green is the present island, and the dark color indicates where the shoreline would be, say 130,000 years ago. The island was about 35% larger, and the shoreline is between a mile and a mile and a half there, 2 miles, 5 miles farther seaward than it is now. So at that time, then this coast would have been more than a mile inland. If you go a mile inland, you don't have any sand to build sand dunes, because there's no beach. The beach is here. There's a white-tailed chopping bird, that's a native. So what's happening to these sand dunes when they're sitting a mile or 2 miles inland? Not much. They're being vegetated, plants are growing on them, and the fine silt and clay that's floating around in the atmosphere from the weathering of the lava rocks is being trapped by these plants in their roots, and they're building soils. So during that time, when everything's inland, soil's accumulating, and you're getting this, you're forming these layers right here. These are fossil soils called paleosols that are forming during that time. And then sea level, if you go back, that would have been, say, there. That's how old these are actually back here. And sea level comes back up, and you have beaches again with sand being formed, and you pile another layer of sand on top of the old soil. So you've got this cycle change. So what we see vertically here along the coast is related to what's going on as the shoreline is moving back and forth laterally, and all these processes are going on. Now, this curve here expands this idea back to about 800,000 years. You can see that there's these 1, 2, 3, 4 cycles that go back to about 435,000 years. And then the cycles never get very high, like that. So the last limestone we see, which is the one in the cave that we see, the bottom of that would represent about this time, about 435,000 years ago. And then sea level came up and deposited the sand dunes and then dropped down and formed the soil and so on. So sea level's going up and down and forming these different layers of limestone and soil. So what we're reading here is evidence of global climatic change related to sea level fluctuation. Just, even though there were no glaciers on this island, there were glaciers on the Big Island, as you probably know, on Makauwahi, but there were probably none on this island. But we see that the secondary effect of climate change and glaciation occurring when you look at this kind of sea levels. I might want to point out too, it's interesting that, if you take this, just the last 435,000 years, I did a calculation here where it turns out that only 15% of the time was sea level within 100 feet of where it is now. Most of the time in the last several 100,000 years, sea level's been much, much lower. Most of the time, it's a lot lower. This is actually on the Earth right now is a bit anomalous in that our sea level is so high. So, just in the last 125,000 years, it's been within 100 feet only 27% of the time. So within 100 feet. You know, if you're talking about within 10 feet, you know, it's really a very minor amount of time. So it's pretty high right now in that respect. So to think that only 15% of the time sea level's been within 100 feet of where it is today, I think that it gives you a better idea of what's going on with the surface of the planet and shorelines and so on. And that's why you can go to Oahu and go down in 300 feet of water and dig up the old beaches down there and dump them back on Waikiki so the tourists have a place to put their beach towels, you know, and bring money to Hawaii kind of thing. So beaches are important economically in that respect. But there's all kinds of beaches out there offshore. You can find them and bring the sand back up. It's called replenishment. Of course, you have to do that because humans have figured out ways to modify the shoreline so their beaches disappear artificially and so on, things like that. So, you know, there's all kinds of ramifications. But so it's, you know, we study where the sand comes from because if you have a beach that's disappearing and you don't even know where the sand comes from to begin with, it's kind of hard to figure out a solution to that. And so that's another part of this story that I've been involved in. So anyway, I hope that was an overview. It was a little bit winded, I know, but I just wanted to point out there's a lot of different aspects. Start looking into this in some detail. And I actually glossed over a few things there, so it's pretty interesting when you start seeing this kind of a record. Hawaii is kind of neat because you can go to Mauna Kea, you can see there interlayered glacial deposits and lava flows. Fire and ice, the real story over there, right? And did you go up to the summit over there when you were there? Yeah, great place to see all that stuff. You can see all kinds of evidence of glaciation. And you can go offshore in the deep sea drilling around here and you can find layers of sediment by looking at the isotope ratios and the skeletons of forams. You can see the heating and cooling of the ocean and you can see the same cycles there. So we've got that same cyclicity that's been documented in many, many different ways in terms of reading the geologic record. And this is just another place, a different approach. Who would think sand dunes would give you information on sea level change? But it's a good example right here.